All right. Hello, everyone. My name's Tom Grace. I'm a space weather forecaster at the Bureau of Meteorology, and I'm going to talk today about the impact of space weather on human space flight. So I'm going to start off by talking a bit about the Bureau. So we have a space weather home here in Adelaide at a place called Lot 14, which is innovation and science precinct with a focus on space. It's full of companies that operate in space, and there's plenty more coming as more and more buildings get put here. It's a pretty new facility. We're a pretty new facility as well. So here at the Australian Space Weather Forecasting Centre, we've only recently moved in. There's forecasters like me here. We've got space weather engagement team as well, and we've got researchers coming in at the end of the year as well to turn it into a full space weather operation center. There's a look inside the forecasting center. That's where I'm sitting right now. Australia have actually been monitoring space weather since 1947 through a project called the Ionospheric Prediction Service. However, the AWFC represents the first dedicated operational forecasting center in Australia. We formed a new team in April of this year, and we launched on the 6th of October, which is a little bit over a month ago. So we are very new and very excited to get talking about space weather. So what is space weather? Well, unfortunately, it's not the weather on Mars or Venus. We don't get to travel that far. What we do look at is the sun. So the vast majority of space weather is driven by the sun, and it's the effect that the sun has on Earth and the local space around Earth, and possibly further afield in the event of humans traveling out into the rest of the solar system. So there's a few things the sun can do which can disrupt the near-Earth space. You've probably heard of things like solar flares, but it can also unleash large clouds of plasma through things called coronal mass ejections. And there can also be gaps in its outer atmosphere called coronal holes, which allow streams of what's called the solar wind, as constant plasma output, to fly much faster through space. So there are a couple of things that can happen on the sun which can affect us right here. And the kind of effects we see are things called geomagnetic storms, radio blackouts, and radiation storms. These are the main things that the sun does that we experience here on Earth. So I'll start off with solar flares. So a solar flare is probably one of the most well-known phenomena that the sun does. Really, really bright flash of radiation, mostly ultraviolet and X-rays. The sun's obviously always giving off light radiation, but flares indicate a large increase in the really high energy light radiation. They travel to us really quickly at the speed of light, unsurprisingly, and take about 8 minutes to get here. So when we measure solar flares and other similar events, we use a scale system called the Australian Space Weather Alert System, which has a G scale for geomagnetic storms, the S scale for solar radiation storms, and the R scale for radio blackout. So the R scale applies to flares. Sorry. So flares themselves send light radiation, which is absorbed mostly by our atmosphere. Our atmosphere does a really good job of keeping us safe from this sort of radiation. However, by absorbing the radiation, the atmosphere actually becomes a little bit harder to penetrate for radio waves, which can cause problems for communication. So that's where the R scale comes in for radio blackouts. And each of these scales are 5 points. They go from an R1 or a G1 or an S1 all the way to a number 5. And they describe the danger that each one poses, with 1 being the least, 5 being the highest. So I'll show you a little video of some of the other things that the sun can do. So a thing called a coronal mass ejection, which, as I said earlier, is a large cloud of plasma being shot out of the surface. And we've got some composite images here that will show you what that looks like. So in the middle of this, we have a picture of the surface of the sun, the photosphere. And then around it, we have a composite of coronagraph images. So these are they're all taken by satellites. And the coronagraph images, the satellites actually have an occulting disk, a black disk over the sun. So they can't see the sun because that's way too bright. They need to see the stuff around it, which is much fainter. So they block out the sun so they can see it. And also on here, we can see the Earth here, that little blue dot in the box up there. That's the Earth to scale. So I'll play the video and you can have a look at what a coronal mass ejection looks like. There we go. Kaboom. I'll play it one more time, I think, just so you can see it again. So you'll see there's bits of solar wind flying away, and then you see, boom, this huge coronal mass ejection get blown out. And then you'll also see that increase in static on the image as well. That comes from high energy particles that have also been ejected, slamming into the imaging disk, the imaging setup on that satellite, and causing that. So a coronal mass ejection causes geomagnetic storms. So to start with, the sun releases one, like we just saw in the image. There's explosion of plasma, creates a shock wave that travels through space, building up as it goes, and it interacts with the Earth's magnetosphere. So it doesn't just sort of hit the planet directly. Plasma is full of magnetic fields, electric fields, and our planet Earth is surrounded by a magnetic field as well. So these magnetic fields actually interact, and that magnetic field around Earth is really useful because it keeps us safe from high energy particles, but it does get changed by giant clouds of plasma. So the plasma transfers a whole bunch of energy into the magnetic field around the planet. And this can have a whole range of impacts. So you can see disruptions to the power grid. You can see depressions in the ionosphere, which is the electron layer in our atmosphere, which is required for certain communications. It also causes auroras. So auroras are one of the cooler things about space weather. The bigger geomagnetic storm you get, the further south or north the auroras will travel from their respective poles. The third kind of thing the sun can do is a radiation storm. So these can come from large flares and large CMEs, and they consist of charged particles, things like protons, in fact, mostly protons, that are sent out towards Earth. Now, obviously, plasma is also charged particles, but these storms are a little bit different in that they travel much faster. So a CME travels maybe about 1,600 kilometers per second sometimes, which sounds pretty fast, but these radiation storm particles can travel up to half of the speed of light, which is very, very fast, and it means that they get here super quickly as well. We don't get a lot of warning with them sometimes. So these particles come from strong solar flares, and they zoom out through space. Now, our magnetic field will do some job in protecting us from these as well, because they're charged particles. So it will direct a lot of them towards the poles. They can cause auroras the same as a geomagnetic storm can. So the highest risk is to astronauts or anyone flying near the poles. However, you're also at more risk the further away from Earth you are, because our atmosphere also protects us from the high energy particles that get through the magnetic shield. So at the surface of Earth, you're pretty safe from this sort of thing, but the higher up you go and the closer to the poles you go, the more at risk you are. Now, not all radiation comes from the sun, so I'm going to briefly touch on galactic cosmic rays. So cosmic rays are basically charged particles like protons, mostly protons again, that don't come from the sun. They come from outside of our solar system, and because of that, they generally actually have much higher energies, and they can come from any direction, and they're kind of always there. They can have super high energy and enables them to pass through 4 inches of lead. And again, our magnetic field and our atmosphere keep us on Earth nice and safe from most of these. And in fact, the sun does a little bit too. So the big clouds of plasma the sun shoots out and the radiation events that come from the sun can actually help to block galactic cosmic rays from hitting us, which is pretty cool because the galactic cosmic rays do have more energy, generally speaking, than the particles that come from the sun. So we'll talk a little bit about the impacts of space weather on humans. So the main impact is radiation. So humans aren't affected by plasma magnetic fields and electric fields so much. And so the ultraviolet and X-ray radiation can be dangerous, but it's pretty easy to protect against it. So the biggest radiation hazards are galactic cosmic rays, solar proton events, the very high energy particles coming from the sun, and high energy particles that are trapped in Earth's magnetic field, which can come from the earlier space weather events as well. Once you're on the surface of Moon or Mars, you're outside of the protection of atmospheres and magnetic fields so much. So you are more at risk from all of these, including X-ray and UV radiation. But a good spacesuit or a good space station or a good shelter will protect you from X-rays and UV radiation, but it can be less effective at protecting you from the particle radiation. So how much radiation are we talking about when it comes to space? So here's a little table that sort of breaks down. You can see that the average population person in the US gets less than 5,000 microsieverts of radiation exposure a year. There are worker limits in place as well, 20,000 microsieverts per year over 5 years, no more than 50,000. And you can see that US astronauts can already experience quite a bit higher than that. They can experience up to 100,000 microsieverts cumulative over the time that they're out there. Which is quite a lot already. But another thing to consider is the fact that of all the people in space, only 24 have traveled beyond low Earth orbit. So most of the people in space, which is still only about 500 and something people, are in low Earth orbit. So they're still kind of protected by the atmosphere, and they're still protected by a magnetic field. So if we want to head further out into space, that cumulative exposure is going to go up. So how do we keep people safe out in space? Well, we've already talked a bit about protective suits and visors for UV and X-rays. That's pretty straightforward. You generally need a spacesuit when you're in space or a space station anyway. So an extra added bonus of keeping all the air in is that it helps protect you from UV and X-ray radiation. You can invest in shielding as well. So the Orion MP CV Storm Shelter is a newly designed crew capsule that's going to go on the Artemis project missions. And they are reinforced and made of special kind of materials to keep out particle radiation. And in fact, there is already a place on the space station that is better protected against particle radiation, which is where astronauts will go if a large proton storm is headed in their direction. Another thing we can do is pick astronauts who are more resistant to radiation. So not a lot of people have been in space, so we're still really at the forefront of researching how space radiation affects people. And it's definitely true that some people are just more resilient than others. So it might just be genetic lottery as to whether or not you're able to go out into space right now. What could be more useful is medication to make your cells more resistant to radiation. We can also put more and more detectors out there to measure exactly what is happening. So that's something that's being done right now. Various detectors and even fake human torsos are being put out in space to see the effects of radiation. An important job for us here at the Bureau of Meteorology is making sure people in space are well aware of what's coming their way, especially if a proton event might be headed in their direction, so we can give them quick updates. Launching your satellites at the right time as well is something we'll touch on in a little bit. And even more possibly, hibernation. If you're headed towards somewhere far enough away, getting astronauts to be asleep and somewhere very well protected on their ship could keep them safe from all the horrible things space might throw at them. Now, I mentioned launching things at the right time. Now, you'd think that the best time to launch things is when the sun is least active. And the good news is the sun actually goes through activity cycles. Right now, we're headed towards a maximum of solar activity. So we're heading out of a minimum. But every 11 years, the sun cycles between maximums and minimums. So you'd think the best time to send crewed space flights out is at solar minimum because there'll be less flares, less CMEs, less proton storms. But that might not be the right answer. As I mentioned a lot earlier, cosmic rays can be blocked from getting to us by solar activity. And cosmic rays have a lot more energy and can come from almost any direction. You just can't forecast them at all. Whereas you can see solar storms coming a lot of the time. So the best time to launch crewed spaceflight might actually be at solar maximum, and then relying on our ability to see the sun and make sure we know if anything's coming from the sun, combined with relying a little bit more on the sun to keep us that bit extra safe while we're out in space. So I'm going to go over a couple of case studies now as we wrap up. So first of all, the International Space Station, obviously one of the most well-known examples of people living in space for long periods of time. The first thing that's worth mentioning about the space station is it's actually really close to Earth. It's only about 400 kilometers above the surface, so it's shielded by the magnetosphere from solar particle events for most of its trajectory. The astronauts on board are are given radiation counters. It's well maintained exactly how much radiation they've absorbed throughout their career. And there's a lot of shielding on the space station as well. However, they're not perfectly safe. So there are particles in or orbiting Earth in things called radiation belts, the Van Allen radiation belts. And they sometimes bulge a bit closer to the Earth than normal. in certain parts of the sky, and the space station can go through those, and in those occasions can detect irregular radiation events, which have also been detected on Mars. And even though they are protected by the magnetic field, for big solar proton events, they can still see an effect like Mir did in 1989. A little bit further afield here, looking at the moon. So the moon's a lot further away. It's 380,000 kilometers away. It has no atmosphere, or no atmosphere worth talking about, and it has no magnetosphere either. So this means it has 300 to 400 times the radiation levels on Earth. There's no magnetic field to deflect all the particles. There's no atmosphere to absorb the particles or the UV or X-ray radiation. So your astronauts need protection against UV and X-rays, as well as some sort of protection from solar proton events. So the Apollo astronauts had protection from UV and X-rays. They had a suit on, kept them pretty safe. Their capsule was pretty safe too, but they weren't really protected against proton events. The protons with high enough energy can easily go through a spacesuit, and the walls of their capsule that they went down were very thin as well. They just sort of got lucky in the sense that there aren't that many proton events, but they did get pretty close. So a few weeks before Apollo 12, there was a major event with about 100 rem radiation before they got there. And then there was one actually between Apollo 16 and 17, which would have hit astronauts with a blast of 7,000 rems of radiation, which is pretty scary. And as I said, they didn't really have a way of dealing with that then, but that's something we definitely want to think about going forward, especially if we're going to look at people staying on the moon for extended periods of time when the chances of an SPE just gets greater and greater. And my last case study is going to look even further afield at Mars. So Mars has a lot of the same kind of problems that the moon has. It has not got very much atmosphere, more than the moon, but not very much, and it doesn't have a magnetosphere. The upside of Mars is because it's further from the sun and it has a lot of dust storms, it does actually get less solar irradiance than Earth does. So if it had the same kind of protections, it would be a safer place to be in terms of space radiation than it is here on Earth. However, it doesn't have that protection, which means it has about 50 times the Earth's surface radiation. And the picture that I've got here shows the capabilities for a Mars mission. And you can see the green dots mean something's been accomplished, yellow means it's on the way, and red means it's not really very close. And you can see underlined here, radiation protection is all reds and yellows. So we're still working, or we still need to do a lot of work on making sure that our astronauts are nice and safe from radiation when they're on Mars. But before I finish up, I'm going to go to a slightly different topic and talk about spacecraft, because people aren't the only things at risk from space weather. Spacecraft can get affected by space weather as well, and I'm sure you're all aware that astronauts kind of need their spacecraft to be working while they're in space. Otherwise, they're in a lot of trouble. So there are three things that I'm going to talk about: atmospheric drag on low Earth orbit craft, surface and internal charging, and solar panel degradation. So first up, space weather can be a real drag. So one of the major effects from solar storms is satellite drag on low Earth orbit. So you can see our little satellite orbiting around the Earth, happy as can be. That's what's supposed to happen. But when you get more radiation coming from the sun, or you get a geomagnetic storm, a lot of that energy gets absorbed by the atmosphere. And when the gases in our atmosphere absorb energy, they get hotter and they expand. And this affects the trajectory of the satellite. It has to pass through all this extra gas, and that lowers its orbital speed, which brings it closer to Earth. Now, it doesn't always just smash into the surface like that. What it basically means is satellites need to spend more of their energy, more of their fuel, keeping themselves up in the proper orbit, which lowers their lifetime. That's something that's worth considering. So charging and discharging can also occur. So when energetic electrons encounter satellites, they can form charges on the surface, and different parts of the craft will get different amounts of charge based on their material. And if the different amounts of charge get big enough, you'll have little lightning strike discharges that zap across the satellite, which can damage systems. This can also happen inside as well. If you have high enough energy things like super energetic protons coming from the sun, these can plow inside a satellite, form charges inside that do the same discharge, which can be even more damaging. They can also cause things that are called single event upsets. And single event upsets is where a proton or something similar actually hits a binary bit inside a computer system and flips it from 0 to 1, which can change all sorts of things. So the space shuttles actually had 4 computers that were built in to negate this. Basically, it meant that if a single event upset happened on one of the computers, the other 3 would be able to deal with that. And they found in one 5-day mission, they had 161 events of single event upsets, which isn't so much of a problem when you have 4 computers, but if you only had 1, it could be a big problem. And the last thing I'm going to touch on is solar panel degradation. So this is caused mostly by protons as well. So solar panels rely on light energy, photons hitting them to provide power, but high energy particle impacts will actually damage the surface of the panels over time. This makes them less transparent as they get scratched, so they take in less light, and they can take years off the lifetime of spacecraft by damaging solar panels. The advantage is if you're in a crewed spacecraft instead of a satellite, you can get out there and fix them or replace them. But the spacewalks are always kind of dangerous, so you probably want to avoid them as much as possible. So it's definitely something, again, that's worth thinking about. So that's it for me on the effects of space weather on crewed spaceflight. Thank you very much for listening. If you have any questions about space weather, don't hesitate to reach out to us at the Australian Space Weather Forecasting Centre. Thank you.